Very much, Abdul. Thanks very much for inviting me. And thank you everyone for joining this last webinar of the series. I also like to thank Alana for arranging this and for creating all the materials to go with this webinar series. So in this final webinar, I'm going to talk about how we can use large language models to help with a task that I'm sure we're all familiar with, which is carrying out literature reviews. I imagine that most of you are probably now familiar with large language models, and I'm sure you've used things like ChatGPT and other tools to maybe summarize documents or analyze documents in some way. If anyone hasn't, we can talk about that in the Q&A afterwards, but I'm hoping that everybody is familiar or has had some interaction with these large language models. What I'm going to do in this webinar is take a step back and look at how these models emerged and what's gone before them and how we used to do things before this technology was available, particularly in the field of natural language processing in terms of computational analysis of documents. When we look at large language models, the problem actually that they were originally built to solve were things like document understanding, so being able to somehow understand the structure of language and documents across multiple languages. And another task, which isn't really spoken about these days, but it's called style transfer. So given the style of a particular type of writing, generate some text in the style of this document or this author. And also machine translation. In fact, that was one of the earliest uses of large language models, was to improve services such as Google Translate. But now, when we see large language models, they're used for all sorts of things, from generating videos and animation, generating fake news. So there's lots of negative connotations of them, but there's lots of positive things about what they can do as well. And in the context of academia, there's a number of tools have emerged that use large language models to automate almost the entire process of carrying out a literature review, from structuring, from doing the search, finding the relevant papers, ranking them, discarding ones that aren't relevant or central to the research question, and then extracting the information from them and comparing them side by side, and then even actually generating a synthesis from those documents for you. But in this webinar, I want to sort of think about, do we actually want to do all this sort of thing? Because in a way, this technology allows us to outsource our thinking to machines. And although that many of us in health informatics have been working towards this goal in a way, I'm sort of wondering now, actually, is this the right thing we should be doing? And do we need to get a balance between maintaining the creativity that's involved in many research tasks we do? I mean, there's a lot of creativity in carrying out a literature review in terms of finding the articles that we want, coming up with our own kind of thesis and synthesis about how we want to put our unique spin on how we see the connections between the papers that we've selected for our review, as well as the more objective stuff in terms of carrying out the quantitative analysis and comparison and statistics as well. So we don't want to take away the creative side and the analysis side and give that to machines. And we also need to have that transparency for repeatability. And we also need to learn. So in this webinar, I'm hoping that we'll look at maybe an approach that combines both, that uses the best parts of this technology, but still allows us to use our own cognitive skills so we continue to learn and we don't end up becoming slaves to these models and having them do everything for us. So that's what I'd like to do in this webinar. So I'm just going to share my screen and we'll start with some slides. Okay, can everyone see this overview?
Yes.
I hope you can. Great. So when we're talking about literature reviews, let's actually sort of take a step back and think about what we're actually trying to achieve here. So we typically have a research question in mind, and maybe we've used a number of databases such as PubMed to find a collection of papers that address this research question. And this will involve quite an iterative process because papers aren't naturally aggregated in collections according to research questions. They're stored according to things like keywords and so on. So we have to be creative in how we come up with a search strategy that's going to help us translate our question into search terms. we won't really cover that here, but this is a sort of something that you'll probably have help with from a librarian to do that process. And the key step after we've found papers that match our criteria for our literature review and our research question is then comparing these papers side by side to compare their methods, their findings, their conclusions. And typically we use a structure called PICO to do this, although this is mostly used in quantitative studies, but it also is valid in qualitative research as well. So PICO stands for population, so who were the study participants, how many of them were there and what were their characteristics, the intervention, what was done with the study participants, the treatment group, and the comparison group, so who was in the control group and what treatment was done to the control group, if any, and then what the outcome and what was the measure of success for the intervention. Um, in the old days, it was hard to pull out this information automatically because abstracts of papers were typically written as a sort of narrative without this information clearly marked. But what we see in more recent papers is that the abstract now is quite nicely structured, having these section headings in there. So it's easier to see at a glance who the participants were, what the intervention was, and what the outcome was. But ideally, we'd like a machine to help us with that process, and we'll look at how that can work. Because if we can structure this information in a way that machines can understand, then we can automate some of the analysis of the paper and help reduce some of the cognitive load without offloading everything to the machine. Typically, we will extract this information manually, and papers aren't written with machines in mind. And so we want to ideally have a process that turns paper into a structure, something like this. Now, this is a machine representation of a paper. It's in a format called JSON. Now, this is one of the things actually I developed starting from my PhD, actually 15 years ago now with Abdul. I was initially looking at how we could translate different types of documents, so clinical guidelines and discharge summaries, into a structured format, so we could do some automated analysis of the data because they were in a machine readable form. And what I did is later on applied that to documents in general and particularly research papers to help with this problem of automating some of the literature review analysis process. So basically we have fields. We have what we have call key value pairs. So we have things like key of the metadata, and then that's broken down into things like title, and then the title, the author, number of pages, affiliations, and so on. Now, this is all automatically extracted by a computational process that has been developed over a number of years, and there's a number of tools out there that will do a similar sort of thing. There's some open source tools out there that I can put into the documentation that I'll send after this webinar that will generate this sort of structure automatically using natural language processing and machine learning to do this. But if we have this structured data, then it becomes easier to write software that can then analyze this and compare studies side by side. And once we can do that, the scaling issue of literature reviews involving hundreds of papers becomes more tractable because we've got them into this standard format. We talked about Pico earlier, so I'll skip that. So how is this done? Well, in the old way, before large language models, this was quite a knowledge intensive process. So it was called knowledge engineering, actually. And we used a process called information extraction, and that would consist of a number of different steps. We'd have a step called document parsing. And what that would do is break the document down into things like headings, sections, paragraphs, and then metadata, such as things like figure and table captions, the references at the end of the article, and so on. And once we've done that high level structuring, which looks like something like this, where you've got all your headings here, captions, and so on, then you can do a deeper analysis of the individual sentences themselves. And so there's tools out there that will do sentence parsing for you. There's a natural language processing library called Spacey, which is written in Python, which is very popular for doing this kind of parsing of text. And what it typically does is breaks information down into their parts of speech as a first step. So you can see from the screenshot here, if I've got a sentence like this that you might see in maybe a discharge summary or medical report, So it's got things like abbreviations like CXR, shows no evidence of pneumonia, continue warfarin for AFib, follow up for management of type 2, and that should say DM there, it's just truncated that. So the first step in a typical old-fashioned, as I will call it, because this is predates large language models, an old-fashioned natural language processing pipeline would do things like this. So it would parse the text into things like the nouns, the verbs, the other parts of speech, prepositions, and so on, and identify the relationships between them. So if you use a piece of software online called a Displacy, you can actually click on this and you can put in any sentence in here and click parse, and it will generate this visual representation for you. And this is how you'd start your first step of your pipeline. Once you've carried out an initial structuring of the document, you then parse the individual sentences and break it down like that. And then from that, you would have a pipeline that would use that information as features in a machine learning model. So the features could be things like the part of speech, the token or the word itself, and maybe the relationship between it. And it would use those as learning features to identify which things were things called entities. So things like diseases, treatments, symptoms, and so on, or things like people, places, locations. And it would use that to learn that information. So that would be the next step in your pipeline, is identifying the entities that you're interested in. And then the third step of the pipeline would be something called relationship extraction. And again, that would be a machine learning pipeline that would find the relationship between diseases and treatment. So it would identify a connection between the mentions of a disease and the mentions of a treatment, and say that this particular disease was treated by this medication, for example. And these were all very task specific. So every time that you wanted to build a pipeline for a particular type of document, so in my case, when I was doing my PhD, I was analysing clinical guidelines and I was analysing discharge summaries. But later on, I was analysing research papers and other documents. But each of these tasks you had to build a separate pipeline. You had to train a new model. It was very specific and so quite brittle. And it involved lots of knowledge engineering, because you'd need domain expertise of the text that you were dealing with, and you'd need obviously programming expertise and knowledge of natural language processing and machine learning to put all these pipelines together and train them and aggregate them. And once you carried out all those steps, you might end up with something like this, where taking that sentence we looked at before about no evidence of pneumonia, continue warfarin for AFib, and follow up with the management of type 2 diabetes. And you'd get something like this. So it would kind of give you a visual representation. So it would identify AFib as actually meaning atrial fibrillation, and it would identify it as classified as a problem, or some sort of thing that needs to be addressed. It would automatically identify type 2 DM as type 2 diabetes, and it would identify things like negated relationships. So things where you're saying there's no evidence of this, or this is not true, or this is not working, or we tried this, it didn't work, or we're not going to do that. So the relationships between things. And negation was a key part of that. You often see this in medical text. You don't always want to know the positive stuff, you want to know the negative stuff. Things like identifying warfarin as medication. So these typical pipelines usually involve large dictionaries of things like medications, dictionaries of diseases, and so on, to do lookup tables in combination with the models that would have to be built pretty much manually and trained manually, with manually labeled data, and it was quite a laborious process. And it was prone to error. And if you wanted to improve your accuracy beyond a certain point, it wasn't always clear how you would do that, other than throw more labeled data at it. But creating labeled data was expensive, because you had to go in and basically this is what you'd have to do. You'd have to go into some software and manually label words and phrases in the way that you wanted the model to recognize them, with examples that it hadn't seen. So you'd have to go through text and swipe over them and say, oh yes, pneumonia is a problem and warfarin is a medication. And then your model would learn these. And because we've had multiple steps in this process, as we saw previously, we had document parsing, sentence parsing, relationship extraction, and then finally the task-specific stuff. um, each the input to each section, to each task, depended on the accuracy of the output of the previous task. So you got compounding errors. So if this document parsing was only 90% accurate and your sentence parsing was only 90% accurate, then the next step you're going into sort of 80% accuracy before you even start your relationship extraction and so on. So each time you would get compounding errors. But that was the way it had to be done until large language models came along. And then, as I said earlier, you had to have particular processing pipelines for particular things. So this is something that I used to do in my PhD, as I automatically identify patient history from clinical notes using some models. The thing we're talking about today, which is extracting problem intervention control and outcome from research papers. And you'd have a different pipeline for things like patents, non-medical stuff. And you'd use tools like this, Spacey, and MedSpacey, which is specific to medical documents. And these tools are still available and they're still widely used because not everyone is going to use large language models for various different reasons, but primarily things like transparency, repeatability, and also privacy. And the state of the art approaches today really combine these knowledge intensive processes with large language models to get the best out of both. And we'll look at how that works. So that was the old way of doing things. And then large language models came along initially just after I finished my PhD in 2012. Things like BERT was just about to come on. I think maybe BERT was a couple of years later. But the research in models like BERT and BART was already ongoing. And, there were things available within the conference is where people were demonstrating what you could do with language models. But essentially, all they were doing really is predicting um, a missing word in a stream of text. So you'd have a sequence of words and you'd mask a word in your training data. So, for example, the student something the book. And the model, the first large language model, which was called BERT, which stands for bidirectional encoding of R, a recursive, I think, transformers. I'm not sure about the R actually. Transformers is one of the things in there, and bidirectional encoding. And it would reconstruct the information by reading both ends of the text. So, given a sentence, it would read from the forward direction, the backward direction, and it typically and the key thing was it was unsupervised. So there was nobody labeling data and manually telling it what to do. It was basically given large amounts of data, and from the neural network, it would learn to reassemble the text by representing the data in a unique way. Now, we're not going to cover the unique way that was designed to do this. It was called the transformer, and it really did revolutionize natural language processing. But there's lots of information about transformers and how they work. But effectively, they have this thing called masked attention, where each word is looking backwards from each word to see its relationship to previous words and following words, and building a mathematical model, typically vectors that represent the word in context with all the other words that surround it. Now, bear in mind this has happened at a large scale. Typically, the web, basically every document's been on the web, and so it's over the course of all this huge amount of training data, it's learned the probability distributions of text to be able to make predictions about what word is in the missing word that we've masked here. Now you think, okay, what use is it being able to reconstruct a sentence given a missing word? Well, because a previous step in this involves creating a representation in a vector format, which can be used to do things like similarities. So you can say the vector for this piece of text with that word masked is going to be quite similar to the reconstructed vector of the complete sentence. And so if we're doing something like a search where we've got an incomplete sentence and we're searching for something, basically the BERT model is going to say, well, I've got all these vectors for all these sentences that I've analyzed, and your search query most closely matches the one that I've reconstructed to be this. And so it can give you a rank list of vectors that are most similar to the sentence that you've input. And so that can be used for things like classification and other tasks typically. So BERT was used particularly for things like discriminative tasks. So give me, what class of documents is this, or tell me, um, if I give you these keywords, what documents is this going to match? And then BERT was extended into something called BART, and the main difference between BERT and BART was BERT was just looking at a single word, so you'd mask a single word and it would reconstruct it. In BART, you would mask complete spans of text. Now, where this became important was things like machine translation and summarization, because if you masked a long enough span of text, then you could use this information to say, rather than giving me the class of documents that this corrupted sentence is most similar to, use it as a basis for generating something that comes next. And so that could be used for things like generating a translation or generating a summary. And the power of these approaches meant that you didn't need to train a new model for every task that you had, because these models could absorb vast quantities of text during training at huge expense, I might add. But because they had such a vast collection of data to work with, they didn't need to be retrained from scratch each time for any particular task. You could use this baseline model and then do something called fine tuning. And what that meant was you'd add a final layer to the model for a specific task. So you said, okay, I want to have a task that identifies medical entities. You would take the off-the-shelf BERT model from Google, which they made available to researchers, because at the time they'd spent millions of dollars building this model. But they gave you the basic model, and then you could say, okay, I just need to do a final layer on top of this that modifies the conditional probabilities of the output given my input criteria. And so you give it a small data set of maybe 1,000 examples that you'd labeled yourself, and that would be the final sort of discriminative layer on top of the standard model. And this was really powerful because suddenly now it opened up natural language processing to a much bigger audience, because somebody could take an off-the-shelf model, so BERT from Google or BART was from Facebook, and you could fine tune it to do specific things. So things like generating answers to questions, summarization, classification, and so on. And some of these models are still in use today. In fact, there's been a resurgence of interest in this BERT model because although at the time it was seen as a large language model, now it's actually seen as quite a small model compared to the massive multi-billion or even trillion parameter models that we see in use today by things like ChatGPT and Claude and others. And so there's been a resurgence of interest to saying, how can we modernize these models to be more like the large language models we use today, but still retaining their small footprint? Because there's the energy used by these massive models is not trivial, and we want to have things that can run on our phones and on our watches. We don't want to have to use this massive compute. And so there's been a resurgence of reanalyzing what these models can do. And actually, people forgot when ChatGPT came out how useful these models were. And we'll come on to some software that uses these still now. I should say this is software that I've built and has been released. I hope you don't mind, but I'll just give you an example of how it works because it is still useful today. But there were still drawbacks with these models, because even though there were general models you could apply to any task with just adding a final layer at the end, you still needed to create that final layer. You still need to do that fine tuning. And you still need to give it documents in that domain. So if you had the BERT model that was generally trained on news documents and Reddit and various other things, if you wanted to use it for clinical notes or clinical guidelines, then you still had to find those documents, fine tune them, label them, and so you still had to do some manual knowledge intensive work, but not at the scale that you used to have to do previously. And these models didn't generalize, and that's why you had to do this final domain specific layer at the end. So then LLMs really came on stream around about 2018, 2019. We had GPT-3 just around about 2019, 2020, and then 3.5 GPT-4 and beyond. I know in many ways quite similar, but they actually simplified things. And this is the amazing thing about large language models, because they actually said, let's just really simplify this task. All we want the model to do is predict the next word, and it works in one direction. So you literally, it's a simplified example here, the student something. Now you can imagine with billions of examples, there's probably loads of sentences, millions of sentences that begin with the student, and there's probably a high proportion of them that follow the next word being read. The student read the research, the student read the book, or something. And so, given the conditional probability of these two words appearing, you can predict using Bayes' theorem, what is the probability that the next word given these two words will be read, for example. And that's basically what the model was doing, really, but with vast amounts of data. And it's doing that each time. So then once it's got the student read, then it's going to predict the next word. So it's almost going to work as a teletype. And in fact, when you looked at the early versions of ChatGPT, actually not ChatGPT, but GPT-3 before it had the chat thing that came out in like 2020, 2021. When you used it, you'd see it going one word at a time. It's like a teletype. It would predict the next word, then the next word, and then it would obviously form a coherent sentence. And how did it form a coherent sentence? What was the magic that you made it think, wow, it seems to understand this? It was really just vast amounts of data that let it do that, vast amounts of data. And the interesting thing was that this word, as we see here, the student read, and it's predicting the next word read, can be applied to any type of data because we can call these things tokens. These don't have to be words, these could be pixels in an image. And if you have a image that's been broken down into sections, into patches of say 16 by 16 pixel squares, you can use the same approach to predict like what is the next pixel going to look like to generate an image. Given an image, say generate an image similar to this, and it's using this as the context to say, okay, the most likely pixel or group of pixels that's going to come next are these. So it could be, or it could be audio. You have a snippet of audio and it's going to predict what is going to come next based on all the vast amounts of data it's seen. And some people say that this is how the brain works, that the brain is just a prediction machine. At its heart, all the brain is doing is predicting what is the next event that's coming to me. Given all the input that comes in visually, audio, touch, um, everything else, internal information from the sensory system, your brain is making a prediction about what event or series of events are going to come next. And obviously then we moderate that with, our frontal lobe and temporal lobes and so on. But essentially, there's an argument among neuroscientists, not accepted by everyone, but effectively the brain is doing a similar thing. It's just predicting what is the next event and then carrying out some action. Now, the interesting thing about this next event prediction is where these things called prompts come in. Now, if those of you that have used large language model will probably be used to typing a prompt. It might be a question. You might give it a question like, what happened in the news today? Or you might say the prompt might be, here's a paragraph of text. I want you to simplify it for me. But all it's doing really is taking that text and using that as the context. So in other words, it's almost using that prompt as the words the student, but obviously much longer, and saying, given this question you're asking me, or given this prompt or this document, what is the most likely sequence of words that's going to come next? And it looks like magic when it runs because you think it's understanding your question, but really that's all it's doing is just sequencing the next most likely sequence of words that come next, given the document you've given it or given the question that you've asked. And where this really advanced things over the previous version of large language models is they didn't need to be fine-tuned. You just needed to give it examples. So you didn't even need to create 1,000 examples of manually labeled data. You just said, I want you to do something like this. Here's an example. And it would go and do it. And so it's this called what's known as few shot or one shot learning, where you just give one example and that's enough for the large language model to see the style that you want it to use. This is where style transfer comes into the picture here, really, because one of the research goals of large language models was not just to predict the next word, but to generate text in the style of some other piece of writing, another document, and so on. And that's basically what you're doing when you're giving it a prompt. You're saying, I want you to do it in this style, like this. And it then goes and does that. The model obviously has been fine-tuned by thousands of workers working for OpenAI, where they've given it examples and filtered out all the bad stuff. But effectively, that's what the model is doing. It's still predicting the next word. So here's an example of that. And you can try this in ChatGPT or Claude. You can try this exact example, and you'll probably get something like this as the result. You can just say this, please identify medical concepts, investigation, problem, medication, along with negated relationships in this sentence. So this is the example that we used earlier, where we'd shown how we'd have this complicated multi-step pipeline to identify these things. But a large language model can just do it because it's seen every piece of HTML that's ever been written on the web, so it knows how to generate the HTML that's behind these color coding schemes here. And it's seen a lot of examples of this type of text, and it understands the context you've given it, so it can generate this information just through lots of examples. And so that same task that we had to develop lots of steps to do something similar using tools like Spacey, a large language model like ChatGPT can do this for us. It can identify the negative relations. It can identify type 2 DM means type 2 diabetes mellitus. And it knows that AFib means atrial fibrillation, just because it's seen lots of examples of this during its training. So you think, great, problem solved. Just throw everything at a large language model, right? Well, not quite. So what happens is something called hallucination. So the more information you give a large language model, you're increasing the search space that it's got to find an answer. Now, these models are trained to be helpful, so they always want to give you an answer, even if there maybe isn't an answer. I know things have changed recently now, and they'll say, I don't know the answer, or I can't answer this. But certainly in the early days, it would say, I must give an answer, even if it's wrong. And so you get stuff called hallucinations, where the model will just generate something which wouldn't be correct. So you've got no way of knowing, and because these things are effectively opaque boxes that we don't really know how they work, not at the individual sentence level at least, we've got no way of sort of fixing these hallucinations. That we just have to accept that there's going to be a certain amount of error. And you just can't just throw a document at the large language model. I mean, you can give it, as we've seen, we can give it a small task like a sentence or two or document. But when we're talking about the scale of literature reviews and the whole search space for a research question where it may need to analyze tens of thousands of documents or more, you can't just give all those documents to a large language model and expect them just to deal with it. And so what I found in my research post PhD was that one way of reducing these hallucinations is to use a combination of the old school approaches with the new approaches to carry out some of those steps to remove a lot of the noise so that the information you're feeding to the large language model is as good quality as it can be. And then you can, and you give it very clear instructions, very specific instructions to avoid these sorts of errors by breaking down the task into smaller and smaller chunks. So it comes back again to this structured format that I showed you before, because if we, rather than starting with a Word document or a PDF, if we give a large language model this, then we've already told it that we've got these sections, we've got a conclusion, we've got methods, and so on. We've got results. And so if we know that this is quite an accurate structure, and we can obviously carry out evaluations, see how accurately we can automatically structure documents using machine learning and NLP. But if we have already got this, then you can break it down into more manageable tasks. You can just send the method section to the LLM. So you're reducing the computational space that it's got to work with. You say, I just want you to have a look at the methods. Tell me about the methods. It's not going to go through the whole PDF. It's just going to zone in on this information. So this can be quite useful if you've already structured your data. You're kind of solving some of the problems of hallucinations because you're being very specific about the data that you want it to look at within each document. You could give it 10 documents and say, here's the method section for each of those. Just look at those, and so on. So that's the first thing you do. The next thing you can do is something called retrieval augmented generation and guided generation. Now, what retrieval augmented generation does is use traditional search and retrieval techniques such as BM25 to take a bunch of keywords or a research question, find the documents, and then just feed in the documents that it's found that most closely match that research question or keywords and send those to an LLM and then say to the LLM, look at each of these documents. I've structured them for you automatically. Go and now and analyze this data. So you're not asking the LLM to go and find something. You're using more traditional approach to do the search and retrieval things. You're extracting the information from it, maybe using LLMs or traditional approaches, and then you're taking that extracted data and sending it to the LLM. And then you can do this thing called guided generation, which we'll come on to at the end. And so the benefit of that is you're kind of looking at the traditional NLP side of things, which typically tends to be quite precise and easily interpretable because you've got a sequence of pipelines that you've either developed using rules or traditional machine learning techniques which are interpretable and analyzable, and you can see how it's fitted the data. And then you're combining that with the power of LLMs. And so it's this typically a four-step process, a bit like the four-step process we saw before, but differently. So you expand your query, you retrieve your documents, you rank the documents in some way, and then you're only in the final step do you get the LLM to process the stuff that you've extracted from traditional approaches. As I say, BM25 is a typical search and indexing technique that's used, or I mean, it could be just basic keyword matching, but a lot of these tools that we're going to look at shortly use this approach to automate the search and analysis side of literature reviews. So let's look at some of these tools. Now, there's this, I don't know if anyone's used this tool called Elicit. It's been around a few years now, but it is absolutely fantastic. But, the big but, is it really does take off the cognitive load. It does do everything for you. I'm not in favor of actually using it for actual real work unless that you actually want to learn about, but it's really great to see how impressive the technology is. So if we had this research question, what are the most effective strategies for COVID outbreak control? Tools such as Elicit, and there's other ones, there's SciSpace, Scite, and Consensus will do that. And what they will do is they will then go and do a search, they'll find papers, they'll break them down into these sections here, and they will analyze each section. So let's have a look at that. I've actually saved a search strategy that I've done in Elicit, which will be in the slide, so you can go and visit it and try it out for yourself. So what Elicit has done is really has automated the review for us. All I've given it as input is this question. It's generated an abstract for me with links to research that I can follow where it's extracted the data. And then it's broken down each of the studies it's selected into study design, what were the outcomes, so back to the PICO thing again, what were the primary outcomes and so on. It's given me tables here. It's all done that for me and broken it down into how many studies it found. This took, it took 15, 20 minutes to generate all this, and then you save the result. But I would say this is doing too much for you. It's really great what it can do, but it's done all that knowledge work for you. So if you were just to do this with all the time, what you're actually going to learn, you're not actually going to read these papers. You're just going to say, oh yeah, so here's my review. And maybe, you're just going to read this and maybe you're going to read the individual tables, but you haven't done the creative part of it yourself. You haven't done the readings, you haven't learned anything, you haven't come up with your own synthesis about how all these things might work together. But on the same time, it is very useful to see the comparison that it has done, but you can't really know how correct this information is without going in and analyzing each one and cross-checking. So is there a happy ground? Well, from my PhD, I developed some software that tried to find that middle ground where it was doing some of the information for you and some of it, well, most of it you had to do yourself. So this is the tool that Abdul mentioned at the beginning. It's called Scholarcy. that I wrote. It looked very different to how it looks now. But basically, you drop in papers, and no matter what the format the paper is in, it always gets turned into this JSON structure here. And so by doing that, it means that no matter whether it's a Word document, a web page, a PDF, PowerPoint presentation, every document gets digested into this card format. And so you've got a nice, easy way of navigating the information by its key findings, its objectives, its methods, results, and so on. You can jump straight to the figures. It's extracted those for you. So it's not done everything for you. It's done enough to help you read and understand the paper and give you some information using traditional NLP, like identifying things like limitations and future work and so on. And also one thing that's using some of the smaller language models for is for things like research comparison. So how does this compare to previous research? So it's doing classification of sentences and highlighting ones that look like where it's comparing with previous research. So it's as consistent with previous reports, we find higher viral loads. So you can then go and check this. You click on reference 7 and you can then go and have a look at it and go and get that paper and read it. So it's doing some of the work for you, but not all of the work. And in doing that processing, it's using traditional NLP techniques combined with large language models to do things like summarizing the key findings. And so I think approach like this is useful because you're able to take each step and check the accuracy. You know, when under the hood, it's doing this JSON generation, which you can check. It's transparent, and then you're only sending the data that you want. So it's only sending the information on the results and methods and so on when it's summarizing each of these things. It's just taking these bits out of the chunks that it's extracted previously. So it's quite a useful way of doing it. Obviously, there's other ways of doing it, but I think that's quite a useful way of combining LLMs with traditional NLP techniques in a more transparent way because you've still got the original paper in front of you. You can read it. It's just been broken down. You've got the full text here. It just makes it a bit more easy to navigate. You've got things like each citation there. You can mouse over and show the findings and so on. So you're not just given a table and kind of taking it on trust. You can say, well, okay, I can break this down. And then if I want to, I can then take all my papers and I can select them and export them to a matrix. So I can export these to Excel. If I export them to Excel, I get something like this, similar to the matrix that you saw in Elicit, where you've got things like evidence strength, contributions, findings, highlights, objectives, and so on. So it's pulled out all those fields in a side-by-side format. So you can see things like the participants for each study and compare those side by side. Look at the limitations of each study, the conclusions and results of each one, and so on. So you can do that as well, but you've still got the original papers there in their full text format that you can read. And no matter what original format they were in, they all go to this card format here. So it kind of makes it a bit easier to read. So that's one way of combining all these approaches into helping with the literature review, where you're still doing the search yourself, you're uploading the papers yourself, but then you're doing the LLM analysis using a combination of techniques. And the software out there called that will do this for you that you can build on yourself. Let's just have a look. Robid, it's called. So this is machine learning software for extracting information from PDF papers. So this is something that you can download and use yourself to build your own type of software similar to this if you want, or something else. This is all openly available, but it's a bit more transparent than closed source things that where you're not really sure how they work. So you can tweak all the models in here. So if you're a programmer, you can download Grobid, you can tweak it, you can retrain the models and build your own analysis pipeline if you want. And then once you've used something like this tool to structure your data, then you can then programmatically send each section to an LLM and get it to pull out stuff that you're interested in, like what were the key methods and so on. And you're doing it then in a more transparent way that you can then, break it down and say, okay, I did this step, I know this step works, I did the next step, and so on. And I think that's a bit more useful than just throwing everything at an LLM and getting it to do the whole lot for you. So there'll in the slides that I'll send afterwards, there'll be a list of the software that you can use to build these types of pipelines yourself. So the final type of way of using LLMs in a way that reduces the mistakes and hallucinations they make is called guided generation. Now, in the software that I wrote, the guide is guided by the guided side is guided by the documents you uploaded yourself, whereas you've selected the text that you want the LLM to process effectively. So you say, upload them, or in this case, I want to select these, and these, and I want to export them to Word or PowerPoint. And at that point, the LLM is only looking at these documents and not anything else. So it's not going to hallucinate stuff that you haven't told it about because you've told it your knowledge base consists of these documents at this point. So that's what's called user-guided generation from LLMs. So you might do the search side of it yourself. You give it the documents and then you get it to do the rest. And this reduces this thing called automation bias. There's a very good systematic review on this by Kate Goddard about the types of biases that result when you hand over all your thinking to machines. You eventually tend to miss the errors that are made because you're so comfortable with the machine working at a certain level of accuracy that you just think, oh yeah, it looks fine, and I'll just go with it. So if you're having to guide the LLM to do stuff for you, then you're always inspecting each step, and so it's less likely that you'll miss it when it makes a mistake because you're not just kind of switched off. You're kind of actively involved. This is kind of another way of describing this is human in the loop generation of LLMs, where you're constantly kind of iterating on it and inspecting the results each time. This kind of user-guided approach can be automated in a certain way, though, and is called pattern guided. And this is where you give a template to the LLM. You say, well, look, I only want you to look at documents that match these criteria. So I want you to generate something, but the output has to be a number, or it has to be structured in this way. And that again forces the LLM to work in a certain way. It gets it to focus its attention just on the information that you've told it to do, and it focuses its output to fit a predefined pattern. There's a website on this if you're interested in more about guided generation. It's quite technical, but it basically tells you how to do this in code. And again, it's using Python, which is like the lingua franca now for AI and NLP. So if you're familiar with Python, then you can use this and build your own guided generation pipelines that help the LLM reduce the errors that are inherent in its thinking by forcing it to constrain to a certain structure. And basically, the goal of this is to reduce the big problem with LLMs, which is hallucinations. And these do actually work very well to a point where you can get much better quality results. And coming back to that tool I showed you earlier, Elicit, that's basically what they're doing. They're using guided generation to ensure that a lot of the stuff that they put in here is accurate because they've given the LLM a template saying, I want you to pull out the information like this and given it examples, and it's given it that structure. So it makes hallucinations much more greatly reduced. I think they published some papers, the team behind Elicit, to show how guided generation can, what is the actual change in accuracy that they can achieve as a result of doing this. So it's worth having a look at the papers that they published on how they've reduced those LLM errors in that way. Okay, so what have we looked at then? We've looked at traditional NLP using complex knowledge-intensive pipelines, which are interpretable, they're precise, but they break easily and they have to be recreated for each different type of document that you're looking at. We looked at some of the early large language models like BERT, that could give you a general picture of how language is structured, which you would then fine tune for specific tasks. And then the modern day LLMs, which work like magic, really, don't they? You give it a document, you ask a question, and it gives you an answer, but they are prone to hallucination. And so we've looked at how things like guided generation, either you selecting the information or you write software that selects information for you by structuring it in this way. Can combine the best of traditional NLP with large language models to get the power of LLMs with the precision of the old school approaches. And I think this is where the direction that is heading for research, really. People talk about neurosymbolic AI as the next wave. We've had the symbolic AI, which is the traditional NLP, the sort of manual, semi-manual approaches for building stuff. We talked about the neural approaches, which is the large language models, but we combine the two into what's called neurosymbolic AI, where we somehow harness human in the loop to continually evolve and refine large language models so they're always learning and always improving. So I would say there's no single approach that was going to work with all problems. You still have to think about the context and domain. You have to think hard about your prompts and how you write them, which isn't something we've covered today. That would be a whole separate talk about how you best prompt a large language model to give you the results that you need. And this is all changing. This is probably out of date now. There's probably new LLMs that have solved all this stuff already that probably going to be announced next week. So this is really fast evolving field, which makes it exciting. But there's always something new to learn. But I think this is the key thing: is somehow can we combine approaches to make the best of our own cognitive skills, our own creativity, with the automation that we get from AI. Can we somehow combine these two so that we're not just handing over our thinking to machines? Thank you very much.